Hello, today I'm going to discuss natural language processing applications in the field of humanities. Over the course of the presentation, we will cover the importance of the technique of NLP in humanities. Next, I'll highlight some common challenges encountered, and then I'll walk through two examples in depth of humanities projects that implemented NLP. Place name analysis in Ukiyo-e print titles with named entity recognition, and then computational authorship analysis using language modeling of the Iliad and the Odyssey. When we think of tech in relation to humanities, the field of digital humanities is often the first thing to come to mind. Digital humanities is a subset of computational humanities, where the goal is to digitize historical artifacts so they can be accessed more widely. They are usually scanned or photographed, and then metadata is created to provide context and information about the item. These artifacts can then be viewed more easily, and the originals can be preserved safely. A large portion of human knowledge is preserved through writing, so when these artifacts' texts are converted to digital, NLP can be a particularly useful tool for this field. It can help with the automation of mundane or even overwhelming tasks that would be difficult for people to complete manually. And in the wider field of computational humanities, researchers use computer processing to gain unique insights to the text of the artifacts. Some humanities experts have wondered if humanities computing can actually provide any insight that a human couldn't just as well provide. But we'll see later in the examples that we cover that humanities computing has indeed been proven to be a worthwhile technique. However, there are some common challenges faced in the field. First is scarcity. As mentioned earlier, artifacts must be digitized before NLP can be applied to them, and this is a very time-consuming process. In many cases, the artifacts of interest may only have limited digitization available. Scarcity may also be due to the fact that there are only a few instances of the artifact that the researcher may wish to study. For instance, there may only be a few surviving instances of a particular ancient author's work, or maybe the language being studied is very rare. Because NLP and machine learning in general requires large data sets in order to be effective, this poses a large challenge in the field. This has led to many NLP models being created for areas of humanities that have large corpora, which biases the tools being created to not be as versatile. Often they don't work on areas that are more niche or are just less popular to be studied, such as non-Western works. This was one of the issues that the researchers ran into in our first example of NLP implementation. For the first example, we'll be looking at a study done that analyzed place names in Ukiyo-e titles. Before we jump into the methodology and results of the NLP techniques used, I'll give some context as to why this project was done in the first place. Ukiyo-e are Japanese woodblock prints from the 17th century to the mid-19th century, and they were created in a way that enabled them to be mass-produced and sold to the public, the most famous of them being The Great Wave by Hokusai. The goal of this project was to be able to use NER to detect place names in the titles of landscape ukiyo-e, hopefully to offer more insight and context to the prints and how society at that time viewed their geospatial surroundings. But one of the interesting aspects of this is that ukiyo-e that depicted landscape scenes wouldn't have been considered as landscapes. In fact, there was no artistic concept of landscapes in early modern Japan like we think of today. Not until the mid to late 19th century would the Western concept of landscapes be introduced to Japan. Instead, ukiyo-e, often thought of as landscapes, are more often meisho-e, which are ukiyo-e that are supposed to depict famous places, with no real consideration given to separating between what was man-made and what was naturally occurring in the environments. Even in this one, a lot of people miss that there are boats with people in them. Instead, these works were meant to emphasize the important aspects of the famous locale, and often focused more on portraying aspects of the environment in a way that was poetic instead of based on the actual topography. For instance, in this ukiyo-e called Sunset Glow at Seta by Hiroshige, the image shows a view of the famous Seta Bridge. The thing is, though, that the view didn't actually look like what we see here. During the early 19th century, Japan faced the Great Tempo Famine, which was one of the worst natural disasters in Japanese history, which is during the time when this ukiyo-e was made. The fact that this area of the painting shows no damage shows how the artist modified reality to make the depiction he created match his intentions better. This kind of adjustment is also seen with this large mountain seen in the background. This is Mount Mikami, but it isn't nearly as tall as shown here. But because it is an important cultural landmark, it has been emphasized by the artist. This sort of poetic distortion is common, and that is why a tool that would be able to aid in tracking places in the ukiyo-e would be helpful in finding more instances like this. The NER could detect place names in the titles of a multitude of ukiyo-e, and the researchers would be able to track what places in Japan were depicted most frequently, and what the distribution of areas depicted in the Ukiyo-e was. This would give insight to what regions and sites were particularly important during that time period. Another useful thing would be able to see what areas are not shown in the prints, since what was left out is also an important indication of how people viewed aspects of their environment during early modern Japan. So for the study, they started by searching for ukiyo-e that had landscape scenes by using the word meisho, which again means famous place. And they isolated over 20,000 digitized ukiyo-e from the 1800s to the 1850s to use. 200 of them were randomly selected and annotated by an expert to be used for the datasets. They focused on getting the NER to recognize two particular entities, GPE for geopolitical entities, which are places that are easily pinned down on maps like cities, temples, and bridges, and then LOC, meaning location, was used for places like roads and mountain ranges that are innately spread out more on a map. This chart shows the amount of each in the datasets as marked by the expert who annotated them. As for the NER system used, they decided to try using the open source NEP library spaCy to see how well its Japanese NER system would perform on the dataset. spaCy's model utilizes convolutional neural networks, a form of deep learning. The results are shown in this chart under the default columns. Since spaCy's default NER system was developed with modern language conventions in mind, they decided to try and fine-tune the system by calibrating the model using another set of 100 prints. The results are shown under the calibrated columns. Precision is how many true positives were detected divided by the sum of true positives and false positives, and then we can also see the sensitivity in the recall column, which is true positives out of the sum of true positives and false negatives. So according to the calculations, the default had the highest precision in the GPE category, meaning it didn't incorrectly assign the tag GPE to non-GPE entities very often. But in the sensitivity, we see that the default scored very low, which indicates that it missed several instances of GPE and also LOC. Then finally, we have the F1 score, which is precision times recall divided by the sum of precision and recall multiplied by 2. And we can see that the calibrated outperformed the default by about 31% in LOC and about 26% in GPE, which is a big improvement, even if it still doesn't get up to the gold standard of 70% or higher that's usually desired in an F1 score. In this chart, the expert's annotation is in green and the calibrated spaCy model is in yellow. When compared to the default model chart, we can see quite a difference. In this one, the annotator is in blue and the spaCy default model is in orange. As we can see, it is missing several instances of both the LOC and the GPE. This is because it correctly identifies entities, but assigns them to these other categories incorrectly. And so we see here some isolated examples where spaCy incorrectly assigned org to an LOC and work of art to a GPE. Overall, the study concluded that the default model alone is not sufficient enough to automate the process of annotations of the Ukiyo-e titles, but that calibrating the spaCy NER model is a worthwhile endeavor because it actually can improve the results significantly. For our next example, the study was conducted to address the Homeric question, which is a question that has been actively considered for over 2,000 years. The Homeric question is the question of whether the legendary poet Homer ever actually existed and wrote the two epics, the Iliad and the Odyssey, originally, before they were collected, reworked, and refined by several poets over the years, or if these iconic poems were always a collective effort to begin with. It is widely accepted that the two poems, as we have them recorded now, are the result of a combination of the work of numerous poets, each contributing unknown portions of varying amounts to the epics. So in this study, the researchers sought to determine the internal similarity of the epics, to see which sections were the most similar and integrated with the rest, and which differed the most. They decided to use character-level statistical language modeling to achieve this, since other authorship attribution and attribution analysis studies done in the past showed this method to be useful. They started by pre-processing the data by converting all characters to lowercase and removing the punctuation. However, they left in accents, since in Greek, especially in poetic meter like dactylic hexameter, the accents change the meaning of words, and since the text is being evaluated on a character level, accents would also be indicators of style between authors. SLM equations are based on the Markov assumption, and they statistically model the probability of what the next character will be. In this study, they used trigrams, which are groups of 3 characters, like in this example of some text from the Iliad. This one 5-character word on its own gives us a total of 3 trigrams. To assess the result, they used perplexity, or PPL, as the measurement, and they used 95% confidence intervals. In this case, a lower PPL means that the excerpt has a stronger relation to the other text. First, they tested the language model on the poems internally. Both the Iliad and the Odyssey have 24 books total, so 24 models were developed per poem. For each, experts from all the books were used as training data except for the one book that the model would be tested on and have its PPL computed. For the Iliad, the second and eighth book had the lowest PPL, which means that they contain excerpts in them that are the most closely associated linguistically with other books. 14 had the highest, meaning it had excerpts with the least linguistically associated. The average in red shows the 17th book as a whole was the least linguistically associated with the other books in the Iliad. The 9th book had the highest average, which means it was the most strongly associated with the other books. For the Odyssey, the 16th book was the book overall with the weakest linguistic association to the rest of the books in the Odyssey, and the 9th book was the one with the strongest linguistic association. What's interesting, though, is that the 24th book has excerpts that are both the least and most strongly associated linguistically with the rest. Things like this is what led the researchers to believe that splitting the poems up by book may be arbitrary and may not be the most useful way to assess authorship, and a smaller unit may need to be used in future studies. The next section, though, was split by book, as they developed one model per each book of the poem to again assess the similarity of books internally to each poem, this time using Pearson's row. Blue represents negative correlation, and red is positive correlation. We can see that there is a strong negative correlation between the 5th book and the 9th book of the Iliad. There's a strong positive correlation between the 1st book and the 19th, and also between the 15th book and the 24th. For the Odyssey, we can see that book 12 shows a lot of negative correlation with the other books, with almost everything in blue. The 9th and 10th book correlates negatively with almost all the other books too, except for their very strong correlation with each other. And books 2, 19, and 24 show strong positive correlation with each other. For the next portion of the project, the researchers studied how well the statistical language models would work as a text classifier, and how it would perform in comparison to human experts, in classifying whether experts were from the Iliad or from the Odyssey. 6 books from each poem were removed to use as the testing dataset. Then they gathered a group of people with varying levels of philology expertise, from undergraduates to teachers of philology in secondary education. They were given several excerpts that they had to classify without access to outside sources. And for the language models, the poem with the lowest PPL computed for each excerpt was predicted as the poem which the language model classified it originating from. Here are the results. This chart shows the accuracy of the language model in red compared to the human excerpts in blue. As we can see, the model performed quite well, only misclassifying 2 excerpts in total. Here is a chart showing the precision, recall, and F1 scores, which shows the language model performed better in all categories except for the recall for the Iliad, when compared against the average of the human experts. Overall, the research showed the Iliad as being more homogeneous and integrated than the Odyssey in terms of its internal linguistic similarity. In the Odyssey, however, 2 groups of books, 9, 10, and 12, and 2, 19, and 24, stand out as particularly similar to each other. Interestingly, they actually do separate themselves narratively as well. The first set is a distinct section of the story where Odysseus describes his adventures on his quest after arriving in Ogygia, and the second set is when the story is set in Hades. Then they also found that when using their statistical language models as a text classifier instead, that the results of the SLM were comparable to the average human philological expert. And that concludes the presentation. Thank you.